Quantum computers operate on qubits, the fundamental unit of quantum information. To process calculations, these physical qubits must remain perfectly isolated, but any interaction with the surrounding thermal or electromagnetic environment causes quantum decoherence, forcing the qubit to lose its state and collapse into useless noise. This instability is the central barrier to practical quantum computing. Modern quantum processors operate with an error rate of about 1 in 1,000 operations. To execute real-world, fault-tolerant algorithms, that error rate must drop to 1 in 1 trillion. Maintaining that fragile stability requires calibration. Engineers must continuously adjust control parameters, specifically microwave pulse amplitudes, durations, and frequencies, to actively correct for environmental coupling and the unintended crosstalk between adjacent qubits. Currently, the math of the hardware is working against us. Errors accumulate inside the processor significantly faster than human operators can calculate and apply these required corrections. To understand exactly how the hardware is drifting out of alignment, researchers cannot look at the qubit itself. They must extract measurement data from these dilution refrigerators and interpret complex two-dimensional experimental plots. This creates a highly manual workflow. A researcher generates a calibration plot, visually inspects the data for anomalies, like sudden spikes or signal drift, and manually tunes the input parameters based on their own subjective expertise. A human expert requires 20 to 30 seconds to interpret a single plot. When a modern quantum lab generates tens of thousands of these plots per day, manual review leads to immediate cognitive fatigue and misdiagnosed errors. To bridge the gap between noisy physical hardware and stable logical systems, research is shifting toward closed-loop artificial intelligence architectures that can manage these adjustments autonomously. In this environment, the challenge of quantum noise has evolved. Stability now relies on the speed and precision of the multimodal data pipelines managing the processor's state. Before integrating an AI into the control loop of a multi-million-dollar quantum processor, researchers had to prove the software could accurately interpret highly complex scientific data. This diagram illustrates the baseline dataset from the Solanki comparative study. Researchers generated 110 synthetic scientific plots containing specific controlled variations, sharp data spikes, continuous signal drift, signal dropouts, phase shifts, and a clean baseline control. When non-expert humans reviewed this data, they successfully identified the anomalies with 60% accuracy, taking an average of 30 seconds per plot. A domain expert with 5 years of specialized experience analyzing these specific curves achieved 95% accuracy, reducing the evaluation time down to 20 seconds per plot. The researchers then ran the exact same dataset through a vision language model, specifically Claude 3.5 Sonnet. This chart compares the final performance across all 3 groups. The vision language model successfully identified the anomalies with 85% accuracy, vastly outperforming the non-experts. The critical metric for hardware scaling is latency. The vision language model completed its analysis in 2.1 seconds, a 14 times speedup over the human domain expert. The model did exhibit specific limitations. It struggled visually with subtle phase shifts, correctly identifying them only 62% of the time, and its internal confidence scores frequently failed to align with its actual accuracy. In an active lab environment, an 85% accuracy rate with microsecond latency is sufficient for first-pass automated triage, effectively eliminating the false negatives that slip past fatigued human operators. Vision language models have crossed the threshold. They are capable of functioning as production-ready scientific anomaly detectors at scales completely impossible for human teams. While general-purpose models demonstrate the underlying concept, active quantum computing environments require architectures built specifically for the unique physics of the hardware. To solve this exact calibration bottleneck, NVIDIA engineered the Ising calibration model. Ising calibration is a 35 billion parameter vision language model built explicitly to read and diagnose quantum processor states. Instead of synthetic graphs, NVIDIA trained the model on real, proprietary measurement data extracted across completely different quantum modalities, including superconducting circuits, complex trapped ions, and quantum dots. This chart details the results of the QCal-eval benchmark, a 6-part semantic scoring test designed by hardware manufacturers to evaluate plot interpretation. The domain-specific Ising model outperformed top-tier general models, beating Gemini 3.1 Pro by 3.2% and GPT 5.4 by 14.5%. The system's effectiveness comes from its ability to assess fit quality and classify outcomes against theoretical benchmarks. These classifications translate directly into actionable instructions, with the model prescribing the exact pulse parameters the hardware needs to test next to eliminate the error. This predictive capability acts as the perceptive foundation for external orchestration frameworks, directly integrating into systems like the NeMo Agent Toolkit. Ising calibration moves the industry into a system that can continuously observe and prescribe solutions for its own hardware. Relying solely on a heavy vision language model introduces an architectural flaw. Reading a plot and planning a solution takes seconds, but preventing quantum decoherence requires applying corrections in microseconds. A fully autonomous system requires a layered intelligence approach, trading processing depth for execution speed. This diagram outlines the classic agent architecture: perception, planning, action, and observation. The 35 billion parameter Ising model handles the deep reasoning required for perception and planning. When the loop reaches the action phase for active error correction, the architecture bottlenecks. The latency of generating a text-based response is millions of times too slow for the hardware's microsecond constraints. The tactical execution is handed off to a secondary system, NVIDIA Ising Decoding, which relies on highly specialized 3D convolutional neural networks. These networks bypass text generation entirely. They process raw syndrome measurement data as multidimensional spatial and temporal structures, identifying error patterns geometrically. To optimize the surface code implementations, the networks ingest highly compressed 9 by 9 by 9 or 13 by 13 by 13 data volumes. This compression yields extreme real-time execution. The networks deliver a latency of 2.33 microseconds per round, processing corrections 2.5 times faster than classical decoding algorithms. The deep multimodal VLM handles the macro calibration of the hardware overnight, while the lightweight convolutional models execute microsecond surface code matching during active computation. Scaling quantum processors to fault tolerance requires both halves of this hybrid architecture: deep reasoning to dictate the strategy, and ultra-fast neural networks to execute the tactics. Deploying this architecture across a multi-device farm allows engineering teams to coordinate multiple independent quantum processors simultaneously. To manage the massive influx of diagnostic telemetry, the system logs the measurement arrays in highly efficient HDF5 binary formats and indexes the metadata through localized SQLite databases. Because the AI agents constantly review this incoming data, they organically learn and document the unique environmental noise profiles of every individual quantum processor. Computing architecture is moving from predefined static instructions to continuous, closed-loop self-optimization. By successfully automating the process of analyzing calibration plots, the industry removes the primary operational bottleneck to scaling hardware. Autonomous agents running massive neural networks can now diagnose and tune the physics of a quantum processor overnight unattended. AI has transitioned from a standard workload into the essential control layer, providing the autonomous oversight necessary to keep the underlying hardware physically stable.